Hello, my name is Stuart Keeler, and I'm going to be talking about Springback. Over the centuries that we have been using sheet metal, the problem has always been one of tears and fractures. But we've learned to minimize these through looking at the deformation through circle grids, forming limit diagrams, through virtual forming, and other technologies. Now, the number one problem is the dimensional stability of variations deviating from the specification. And that comes from the elastic stresses, not the plastic deformation that we're used to, but from the elastic stresses which originate in the atomic cube right here, which is the smallest structure of metal. These atoms are in a certain array, their distance, they are in balance, and they like to stay that way. When you start to deform metal and you start to put a force on it, the first deformation that starts is the elastic deformation, where you're starting to spread these dimensions here on your atomic cube. And this creates the elastic modulus of the steel, also called the Young's modulus. Now, normally this modulus is so strong, 30 million for steel, for example, that it comes right up this axis right here. I've elongated this axis so that we can have some tip in here so we can see what happens to this modulus as we work. Well, as you pull the metal here, you climb up. When you release the forces, it snaps back down. At one point, however, you reach a distance where you have both elastic and now you start with permanent plastic deformation. And this is often dictated by a line which goes parallel to the elastic modulus, offset by 0.2%. You come up here and you write that mark, and that is the yield strength. And if you take this down straight, this is the elastic portion of what you have in the metal up here, and this is your plastic motion, deformation. So you can see that you have a major portion of deformation all tied up there. Another way to determine the yield strength is to do a line which is offset 0.2% and take that line and draw it upwards, and where it intersects this modulus line is the yield stress. Other countries take a 0.05% strain, draw a vertical line, and where that crosses, that's the yield strength. These two ways are about the same for most of the metals, but that's how you determine the yield strength. This is in the elastic region. Now this has the plastic region plus the elastic region. You don't get rid of the elastic region when you're under force. Now the Springback, fortunately for us, is proportional to the yield strength. So if we have a yield strength of 25 KSI and we have a certain amount of Springback, we double to a higher strength metal and we come up to 50 KSI, and now we have doubled the amount of Springback. So as the steel gets stronger, Springback increases, your residual stresses are increasing, and you have to pay more attention to how you correct these things and get back to the dimensional specifications that the customer wants. Now, before the advanced high-strength steels, we had 25 KSI, which is, in this case, would be an AKDQ steel, or a mild steel, which is the global definition. This is the high-strength low alloy steels, 100 KSI. you have 4 times the amount of springback. So if you're making a bend over here, you had made 2 to 3 degrees of bend springback. Now you're talking 8 to 12. Now comes the advanced high-strength steels, which number 1 is the martensite, the martensitic steels, which in this case has a yield strength of 200 KSI. Very, very strong. And now this is 4 times, 8 times what you would find with a mild steel, and you're having 16 to 24 degrees of potential bending and springback. And that is a tremendous problem that you have in creating a stamping to specification. Now, that is determining at this point here at the yield strength. But we do not make very many stampings that all have no deformation in them, just the sheet of metal. And so when you start to deform them, to stretch them, to pull them over punches, or punches pushing them down, you now have an increase in the strength of the material. The yield strength increases, but the elastic portion goes along with it because you're adding more force, you're adding more elastic stresses. And now, instead of this amount of springback in the stamping, you have this much. So you have increased your springback. So part of the stamping that maybe over here has a certain amount, more over here, less over here. And now you have a distribution of springback, which then has to interact until it reaches a balanced condition. Well, that would be nice if everybody had A to B, okay? It would be very nice. However, there are things that where you go that you have stampings going up to C. You might have a strain gradient, which goes up or down as changes in the die or changes in lubrication or the temperature or the speed or whatever. And so you're bouncing back and forth up in here. And this is also a reason where you get this deformation from a gradient, which is a sharp localization of deformation, often on a character line or something like that. So now we have this from it, and you can see why this springback is a real problem now because of this elastic stresses, which we can't measure and we can't see them. Well, it even depends upon the modulus of elasticity. For steel, we have a 30 million modulus, and we have this amount of springback. For a aluminum or a non-ferrous metal, which is 1/3 the modulus at 10 million, has now 3 times the amount of springback. And so the springback depends even on what material you are going to use. Number 1 headache, as far as I'm concerned today, is springback. And we're going to have to find ways to compensate for that. Thank you.